Backing up 2 pages, let's recall what we did. We defined the script Hamiltonian as a kinetic plus a potential energy with a harmonic oscillator, p squared over 2m plus 1/2 kx squared. We inserted the definition of omega here rather than use k, where omega is the square root of k over m. We then defined 2 new variables, x and p, in terms of capital Q and capital P, new position and new momenta, by these factors. We resolve these 2 equations, substitute them in here, and we get the following equation for script h in terms of capital P and capital Q, which reduces down to this equation here. And we write this as 1/2, we'd write this as script h is capital H times h bar omega. So we pull this h bar omega out, and this other 1/2 p squared plus q squared becomes our h. The commutator between q and p becomes just an I, so we've eliminated position. We then are able to take position by analogy with our previous results, position, eigenstate, and act with momenta, and we get this derivative with respect to capital Q. And therefore we are able to actually form a differential equation by letting Q hit H times U, and let Q hit both sides of this equation here, and we end up with E times the function U as a function of capital Q, and on the other side this differential equation, which is a Schrödinger equation for the harmonic oscillator. Now those are the definitions. We now, in terms of those definitions, we define an operator A, which is by definition 1 over the square root of 2 capital Q plus IP, and A dagger 1 over the square root of 2 Q minus IP. We then find the commutation rules between the A and the A dagger, and very quickly are able to show that their commutation rules are 1 between A and A dagger. We're also able to show that this H operator, which is 1/2 p squared plus q squared, is 1/2 AA dagger plus A dagger A. And we go through and actually work this out. And this follows from the fact that we've got, we can actually take P and P plus IQ, Q minus I, Q plus IP and Q minus IP, put them in here, and work out these 2 forms, and you can see that we get, we're able to show that this is exactly Q squared here times 1/2 and 1/2 and P squared over here, and that there is a, and that the opposite terms QP right here cancel and PQ here cancel. Therefore, we've proved that that the Hamiltonian H, apart from h bar omega, can now be written as p squared plus q squared. We define a new operator here at this point, capital N, as A dagger A. And one can very quickly show that the Hamiltonian H is N plus 1/2. And the reason is that H is 1/2 of AA dagger plus A dagger A, so we only have to take this AA dagger and convert it around by using the commutation rules here and get an A dagger A plus 1, and then now we have 1/2 of A dagger A and 1/2 of A dagger A, so we have 2 of them. So this gives us A dagger A plus 1/2, and we've proved that this is the new form of the Hamiltonian. Finally, we want to be able to show what the commutation rules are between capital N and A dagger. And we can derive N with A as we put N here and just do the commutation rules and reduce it down. Here we have A dagger A times A, and then A times A dagger A with a minus sign. We're able to, in order to get this term and this term to cancel, we want to take the A dagger A and interchange them, which gives us a minus 1 plus A dagger A times A minus A dagger A I believe this should be minus 1 plus, this dagger should be over here. Therefore, this is a minus 1 times A, and this term here, A dagger A, cancels with A dagger A here with the opposite sign, leaving us with A, the commutator of n with A is equal to a minus A. Likewise, we look at the commutation rules between n and A dagger, and we do exactly the same structure, and we're able to show here that we get A dagger. So we have the commutator of n A dagger is equal to plus A dagger, as opposed to the commutator of n with A, which is minus A. So let's summarize how we have recast this algebra. We now have 4 elements in the algebra: A dagger, 1, and n. The commutator of A with A dagger is 1. 1 commutes with all the other elements. N is equal to A dagger A, but we're going to pretend that we don't know that in just a minute and treat this as a whole new operator. We know we have been able to derive that NA is minus A. Commutator of n with A is minus A, and the commutator of n with A dagger is plus A dagger. So we notice that the A and the A dagger function exactly in the role of the raising and lowering operators E, plus, and minus if n has the role of the Cartan subalgebra along with capital 1, or along with the element 1, which it will. So those are the new elements of this algebra, and we want to prove now a couple of interesting results. We want to imagine that we have eigenvalues of the operator n. So n times nu is going to give us nu times nu. And we're going to assume that nu is greater than 0. In other words, it has a positive norm, and in fact we're going to give it a normalization of 1 a little bit later. We now want to take nu, A dagger A, nu, and we know that that's equal to n. Therefore it's equal to, as n acts to the right, nu times nu. Next we want to take nu, A with A dagger, like this. By inverting these in their normal order, we can rewrite that as n plus 1. That's because that is A dagger A is equal to n. So writing it this way, n times nu gives us 1, gives us nu, and 1 times this gives us 1 times nu projected onto nu. And we're going to use those equations in what comes up next. We next look at the following construction in our harmonic oscillator LieAlgebra. We take A times nu times its conjugate in the dual space, which is the bra vector nu with an A dagger acting upon it. And this product we know already is nu times nu. That's because A dagger A acting to the right gives us exactly the eigenvalue nu. This object right here must have a positive norm, and this object here must also have a positive norm. It follows that nu itself must be positive or 0. And it can be 0 only in the case that A on nu gives 0, because a vanishing norm means that the vector itself is 0. Let me repeat this again. By taking this construction here, we can think of A dagger and an A as forming the product of this vector and its dual. Now the product of a vector and its dual must give us a positive norm. Likewise, nu with itself must give us a positive norm. So this whole side is positive and this is positive. It follows that nu has to be positive. It has to be greater than 0. The only way it could be even 0 is that A acting upon nu is equal to 0 itself. Now if nu is equal to 0, then A nu is equal to 0. And if not, then A nu has a norm of nu times nu nu. That's because by looking up here, we can see what the norm of this vector is. It is nu times this. Now we're going to do a similar construction to this one, but rather than taking A dagger A in the middle of two vectors nu, we're going to take A dagger, which we do right here. And so we can look at nu, A dagger nu, and say, what is the norm of this vector? Well, this right here is equal to n plus 1. By redoing the commutation rules, A dagger is A dagger A plus 1, but A dagger A is n. And when this is inserted in here, n has the eigenvector nu, and the 1 comes out front with a nu. Consequently, A dagger nu, this vector right here, has a norm of nu plus 1, nu nu. We now note that A and A dagger are raising and lowering operators. That is, n times A times nu is equal to, by taking the commutation rules, A n minus 1 times nu, which is nu minus 1 times A nu. Therefore, this vector right here, A nu, has an eigenvalue of nu minus 1, corresponding to the operator n. This implies that A times nu, at least apart from normalization, is the vector nu minus 1. Likewise, we can do the same type of construction here with n and A dagger. By reverting these, we can see that this is A dagger n plus 1 times nu. This has an eigenvalue nu plus 1, which moves to the outside here, whereas A dagger now hits nu. Consequently, this implies that A dagger times nu has to equal to nu plus 1, one higher eigenvalue. Well, now this is very reminiscent for the position and the momenta. You recall there, the momenta could be used as a raising operator for position, which actually could be done infinitesimally, and it would therefore translate you in the space. And that's in general what these E plus and E minus operators do in Lie algebra theory. They move us over different states, different admissible states from one to another. We could in fact take A to the P power times nu. For larger and larger P, this gives, obviously, nu minus P. In other words, it will lower the eigenvalue of nu by the value P. Well, now eventually, P is going to be greater than nu, so that has to be 0. So eventually what happens is if I keep hitting a vector nu with A and then another A and another A with higher and higher powers, we're going to get the fact that this vanishes. Well, if this vanishes, it follows that nu must be equal to the integer P. But the set A dagger P is unbounded. Thus the eigenvalues are 0, 1, 2, all the way up to infinity as I go in the other direction and go from nu is equal to 0 to nu is equal to 1, 2, 3, 4, 5, all the way to infinity. So now we've been able to use the eigenvalues and the norms of the vectors in order to show that there is a lowest eigenvalue, namely corresponding to n having an eigenvalue of 0, and then n can be raised using the various A dagger operators so that you go over the entire spectrum of all the possible integers from this lowest one to higher and higher and higher values in an unbounded way. Let's now work on the normalization of these vectors. Now we recall that nu, A dagger nu, was equal to nu plus 1, nu nu. Well, let's begin and assume that our first vectors, 0, 0, the lowest possible eigenvectors of capital N, are already normalized with a normalization equal to 1, so that 0, 0 projected on itself is 1. Then it follows that the next vector, a dagger times nu, right here, will have a normalization which must be the square root of this number here, and nu there is 0, so we have 1 over the square root of 1. Again, let me go through that. If we think of this vector here times its complex conjugate vector, which is this right here, the total product of the vector with itself has this normalization of nu plus 1. If we begin with nu is equal to 0, which we've done here, and taken the norm of that to be 1, it follows that the vector times itself, in other words the square, has an eigenvalue of 0 plus 1, or 1. Therefore, we must take 1 over the square root of 1 in order to get the eigenvalue. The next one of those, as we go up, is going to have to be multiplied by 1 over the square root of 2 times 1. Then 1 over the square root of 3 times 2 times 1. And in general, the nth eigenvalue with a dagger to the nth power from the lowest state must have a normalization in order to maintain its normalization, must be 1 over the square root of n factorial. This will then give us the vector n times the vector n prime is 0 unless those two vectors, both n and n prime, are the same, in which case we get a normalization of 1. It's helpful if we think of what these vectors look like in a matrix form. And so let us go to the matrix form of these vectors, and we can see that n as an operator, where we think of the nu vectors as nu is equal to 0, 1, 2, 3, 4, 5, and going down, the n operator never takes you away from a given eigenvalue of n, and the eigenvalues are listed here as the positive integers going down the diagonal. So n times the vector nu is nu times that vector back again, which is exactly what we've expressed here. And there's no transition that's off diagonal between one state and another. By contrast, the operator A takes any given state and lowers it 1, which we can see here, as this would hit 0, square root of minus 1, all zeros. As this hits the second state, it takes it down to the lowest state. Likewise, when we hit the lowest state, we can see that that is 0 times the next state down. In other words, it vanishes. A dagger, by contrast, takes any one of these states and raises it by the square root of the n, which is the normalization that we just found here. As we go forward from one state to the next, to the next, to the next, each one has a normalization of 1 over the square root of the eigenvalue of the one below it. So this is what n, a, and a dagger look like. And one can verify this by actually taking the commutation rules of n, a, and a dagger and verifying that this matrix representation is a realization in terms of discrete infinite by infinite matrices of the commutation rules. I mentioned that that's sometimes called, if we take such matrices with all products of those, that's sometimes called the enveloping algebra. It's more than the original algebra. It consists of all possible products of the matrices. Now, by reconverting back to the original basis, we see that we have script h is n plus a half times h bar times omega. Q is equal to this form right here in terms of a dagger plus a, and P is this vector here, a dagger minus a with an I out front. This now gives us the correspondence between the original P and Q and script h and the n, a dagger, and a that we have been working with here. We have now solved the problem of the harmonic oscillator using the Lie algebra in the energy or the Hamiltonian eigenvalue representation. But we want to take that in order to visualize it and project it back into the position eigenspace. Now, how do we do that? Well, we really want to take it back because our intuition of the world and our senses are constructed really from our position space in four-dimensional space-time. So we want to project this new vector, which is the eigenvector of h, or actually the number operator n, back onto a position eigenvector. Now we recall that a times nu is equal to 0. And incidentally, the tricks that we're involving here give us some clues as to how we might work problems in Lie algebras that we haven't encountered yet. So be particularly astute of the types of tricks that we're doing. We will actually start here, I emphasize, with a times nu is equal to 0. That's the simplest possible equation we can have because a destroys this state and we end up with a 0 on the right-hand side. So I take this relatively simple equation and project it onto a y basis. So I have y times a times nu is equal to 0, which, writing out what a is, I can write this as 1 over the square root of 2 q plus ip. Well, going back and converting the capital Q and capital P into the regular position and momenta, we see that we get this equation here. We bring in this factor. I take the 1 over the square root of 2 outside, and I bring in this factor here, square root of m omega over h bar, and an I times 1 over m omega h bar here. Now as I move the y through, it hits the q, and I simply get the eigenvalue y. When q hits y, I simply get y, which I get right here, times that factor. When p hits y, I get a minus ih bar partial with respect to y, times I that was already there. Then the y hits the nu directly, and this allows me to form the differential equation for this space, because remember, this whole equation is equal to 0. Simplifying this a little bit, we can see that we have the square root of, from this term right here, we have a minus I times an I, which is 1, h bar here, we have divided by the square root of h bar, so we end up with the square root of h bar over m omega, which we can see from right here, times partial with respect to y of this function, plus this other term, square root of m omega over h bar, times this is equal to 0. Now by multiplying through by this factor here, we then get a much simpler equation, partial with respect to y, plus y of this function is equal to 0. And this has the a solution which is simply a Gaussian. The fact that this term disappears here can be seen by a change in variable, because this is the inverse of this term here. So if we change y to this entire expression, we find that this equation becomes partial with respect to the new y plus y under this function vanishes. And the Gaussian, with a 1 over the square root, 1 over the 4th root of pi normalization, gives us exactly the solution there, which is e to the minus y squared over 2, which is very easy to see.